All right, so that first little bullet point is a review question. How do we get a derivative? You just took a quiz on it. All right, well, it's limit as h goes to 0, good, of x plus h. I view it like steps. That's step 1. Minus the function over h. Perfect. So you do need to know that. That one was review. Now that gives you the derivative. So you would get something with an x in it. So your derivative would be like 7x plus 3 or 5x minus 2 or whatever. If you wanted the derivative at a number, you would then have to plug in that number. So this other definition lets you skip that step and it will just spit out the answer at you. You won't get something with an x in it. You'll get a numeric result. So it's the derivative at a specific point. So it's limit as x goes to c. And it kind of looks weird when it's the in general version. C will be a number. It will be limit as x goes to 3 or whatever it is, right? It is the function f of x minus f of c. So like if it was 3, you'd plug in 3, just whatever you get, over x minus c. Now, I don't want you to view these two things as totally separate pieces of information or like it's all individual, because it's all connected. Let me cover up limit. What does this look like? Because it should remind you of something. Slope, very good. Doesn't it look like change in y over change in x? You subtract the y values and subtract the x. Very good, because that's what it is. It's slope, that's algebra. We put a limit in front of it. Now it's calculus. Okay, it's slope. You aren't sure what the answer is? It's probably slope. That's like what half the class is. Okay, so for number 1 here, find the derivative at 2. Instead of finding the derivative and then having to plug in 2, we're just going to jump straight to the answer. So it'll be limit as x approaches 2. And it starts out with just the function, f of x. So literally just copy that. It's 3x squared plus x. It's kind of like, hey, Ms. Cole, it looks like you just rewrote the problem. Sure did. All right, minus, and this would be f of 2. So we're going to plug in 2 and see what we get. All right, so we're plugging in 2 to this function. 2 squared. 4 times 3, 12 plus 2, 14. So 14 is what goes right there. So it's the function. If you want to use parentheses, I guess you can, but we're going to factor this in the next step, so I don't want to confuse you, but it's the function minus, and then whatever you get when you plug the number in. All right, and then over x minus 2. As a heads up, these will always be indeterminate. It will be 0 over 0 if you plug in 2. You're going to have to get something to cancel out. So limit is x goes to 2, and we're going to factor this. And so how would you split up 3x squared? It's like, welcome back to algebra. Well, yeah, and I do that as well. Like one of them is going to have to be an x minus 2. Like that's going to have to be one of them if you use that to help you. The other one's going to be 3x. And it's going to have to be a 7. And it'll be plus 7. The insides give you plus 7. The outsides give you minus 6. 7 minus 6. That's how you get 1 in the middle. So these cancel. If you didn't write limit, you're probably going to forget what to do next. So what's your last step? Plug into, okay, so f prime of 2, instantaneous rate of change, slope of a tangent line at 2, will be what? What do you get if you plug in 2 to that? 13. Okay, so we got the derivative at one specific point. Now we're gonna get into differentiability, which is this last like big vocabulary word that we're gonna talk about. Is this function continuous at 3? Let's review our definition of continuity. This is from like the very first like calculus lesson we did. You need 3 things for continuity. You need what? A point, a limit, and you have to do them from the both sides, and they have to match. They have to agree, okay? So first, let's try and just plug in 3. Which piece of the function will you plug 3 into? Yeah, why the second one? because the equal to, perfect. All right, so if you plug in 3 there, what do you get? 7, beautiful. We have a point. Now we're gonna do the limit x goes to 3 from the left and the limit x goes to 3 from the right. Please let me not write all over everybody's test. Limit question mark, limit question mark, limit question mark. You need limits, left and right. Which piece of the function do you use for the left? First one, good. X squared minus 2. And for the second one, 2x plus 1. Essentially, all you're doing is plugging in 3. But the notation, they'll take off if you don't put it. Like if there isn't limit there, they won't give you the points. All right, so if you plug in 3 for this one, I know it's from the left, but you're still just plugging in 3. What do you get? 7. And if you plug in 3 to this one, you get 7. So there's a point, there's a limit, and they agree. So the overall answer to the whole thing is yes. After all that, your answer is yes. Yes. Well, if you don't have all this work to support it, this is like the answer and this is the justify part. So yes is the answer, but this is like the justification. Okay. I know justify is a really scary word to see in math class. It basically means show all your work. All right, B, is the function differentiable? That means you have to check the derivative from each side. So we're going to use this formula that I just showed you, and we're going to approach 3. It was 3, right? 3 from the left and 3 from the right. And so you have to learn that new formula, but it just looks like a slope. It's f of x minus f of c over x minus c. So again, which piece of the function do we use for the left? Yeah, the top one. So just copy that, x squared minus 2. Hey, Miss Cole, looks like you just rewrote the problem. Yep, that's what I did. So it's the function minus whatever you get when you plug in 3, and hint, we already did it in part A. What do you get when you plug in 3? 7, good. And then over, what'll go in the denominator? X minus 3, cool. And we're gonna work that out, but let me set up the other one first. So you want the function, if you're going from the right, you want this piece of it, so 2x plus 1, so just the function, minus whatever you get when you plug in 3, which would also be 7, and then over x minus 3. And again, as a heads up, they're all going to be indeterminate. You're going to have to factor and get something to cancel out. So let's do the first one. Limit x goes to 3 from the left. What do we really have there in the numerator? Good, it's x squared minus 9. How's that going to split? Good. So these cancel. And when you plug in 3, 3 plus 3, 6. Let's remember what a derivative is. A derivative means slope, okay? That means the slope from the left is 6. Hold on to that because I'm going to circle back to that. All right, down here, limit x goes to 3 from the right. What do we really have in the numerator? Like if you combined like 2x minus 6, what can you do with that? 2. Good, and you'd be left with if you have 2x minus 6, if 2 and then parentheses x minus 3, which cancels, and so you get 2. So the slope from the left is 6. The derivative from the left is 6. Slope or derivative from the right is 2. So is it differentiable? No. And here's a visual of what's happening. Go back to the piecewise function and look at it. This first piece would be what shape? A quadrat, a parabola. And then they do meet up because it is continuous. They're going to link together, but this piece is linear. So do you see how right there you get like that sharp corner piece? slope from this side is 6, slope from that side is 2. Okay, so that's what's not differentiable, is like, that's what that word means. It's not differentiable at that point. And so I have a big space, we're gonna draw some pictures. Hey, oh, question, go ahead. So there are, like, if the stars align, you can get a quadratic that leans into a linear and it will be differentiable there if those slopes match up exactly. Like if your line that matched up there kind of kept going, they will throw those at you. So yes, it can be differentiable. You have to actually check. Okay. That's a really good question. Thank you for bringing that up because I probably should have said that. So yes, that sometimes it can be, right? So a function is differentiable if there are no discontinuities. And I can't spell and talk at the same time. No discontinuities. If the function's discontinuous, like if it's broken, you can't get a derivative there. Is that, can I say obviously? Like, is that a hopefully obvious thing? Like if it's not continuous, it can't be differentiable. So let's list out what our pictures of discontinuities look like. You can have a hole. You can have a hole with a floating point. And those are both called what? Remember taboo? What do we call those? Removable. Good job. And then what are the non-removable? There's two types of non-removable. Yep. Oh, you guys got them both. A jump, like it's actually broken, or an asymptote. So if you have any one of those things going on, the function's not differentiable because it's not continuous. So you can't get a derivative at a point where there's not a point. Obviously, I don't like to say obviously often in calculus because it's a hard subject, but I hope I can say obviously enough. It has to be continuous. All right, and as we just looked in that previous example, no sharp edges. So the two ways that that can look would be what's called a corner, which would be like your absolute value type graph. And then this thing, which is called a cusp, C-U-S-P. That's how I draw a picture of a bird flying. But instead of a corner, it's like both of the pieces kind of come in, but a sharp edge is what that is. Usually everyone remembers those. No discontinuities, no sharp edges. The third one is the one people forget about. It is no vertical tangent lines. The reason you can't get a vertical tangent line is, hey guys, what's the slope of a vertical line? Undefined. It's like by definition, undefined. All right. So if the graph looks something like this, like it goes vertical in the center there. We drew some pictures of that last time when we were graphing the derivatives, but maybe stars next to that one. That's the one people forget about. And it's like a by definition kind of thing. It's just literally undefined. So you can't get a derivative there because it's undefined. Cool. We're doing good on time. This is generally a really short lesson. I am going to put something up here in the margin. All right. And this is important to know. So if a function, oh, and can I use abbreviations so you don't have to write out differentiable and continuous over and over? Can we agree that DIFF is differentiable and CON is continuous? Okay, cool. If a function is differentiable, it is continuous. So if you get told, and this comes up on the AP exam a lot in the free response part, they will tell you a function is differentiable. And then when you do your justifications of things, you have to say, since the function is differentiable, it is also continuous. So you have to like say that. You get a point for saying that. All right. Now, the opposite of that is not true. If a function is continuous, it is not necessarily differentiable. It might be, but it might not be. So if your function is continuous, it just means that it links up. It may or may not be differentiable. And you can flip your paper over and look at the one we just did where you have the parabola and then the line where they meet. It's continuous, but it's not differentiable. Okay. Everyone's like throwing their pencil down on the table. We're not done yet. We're not done yet. We're going to talk about continuity and differentiability for the following functions. As a heads up, this will involve limits. When you write it on the AP exam, limits from the left, limits from the limits question mark, limits question mark, limits question mark. Okay. What do you think about this as far as continuity? Is this function continuous? Okay, good. So continuous, negative infinity to positive infinity. Because what happens is I bring in differentiability and then people start messing up continuity. And something that you knew before, you still know it now, it didn't change, still continuous, okay? Is this function differentiable? No. So we're going to say not differentiable at x equals what number? 0, good. And so we're going to do a limit from the left of 0 and a limit from the right for 0. That's your justification for why it's not differentiable there. So limit x goes to 0 from the left, limit x goes to 0 from the right, and it should look like a slope. y2 minus y1 over x2 minus x1. So it's going to be the function minus f of 0 over x minus 0. And that's what you can just write for both of them. It's just a definition. That's how that formula looks. So watch me point to it. What is our slope from this left side? What is the slope of this part? -1, good. And the slope of this part, +1. And so the reason that's an acceptable justification is because you're showing those don't equal each other. Okay, cool. Let's do the next one. Is this function continuous? No. All right, so discontinuous at x equals 2. And if you want to dot in the asymptote, bless you, so that you can see it, because I know it's invisible, so it helps if you can see it. Limits from the left, limits from the right. Bless you. Limits, 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 limits. Now for continuity, it is not this. This is a derivative. For continuity, it's just the function. This is back to like unit 1 that we did. So what is your limit as x goes to 2 from the left? Where is this headed? And the reason you're allowed to put negative infinity is because it's sided. As long as it's from just one side, you can put that as an answer. Otherwise, it's DNE. And then what's your limit as x goes to 2 from the right? Positive infinity. That's an acceptable justification because you're showing that those are not equal. Hang in there with me. We don't have too much more to do. Now, since the function's not continuous, it's also not good. Okay, stick with me. Not differentiable at x equals 2. And I'm doing this as a compare and contrast so you can see the difference between how you write the justification. You're still going to do limit x goes to 2 from the left and limit x goes to 2 from the right. But now it's that formula I just showed you. Now it's an actual slope. We're doing a derivative. Well, we're showing that a derivative can't exist there. But it would be f of x minus what? What would come next? F of 2, good, over x minus 2. And that's what you can put for both of them. And if you feel like you're writing the same thing over and over again, yeah, sometimes mathematics is like that. And these don't exist because there's an asymptote there. You can't get a derivative there. Yes.
Is it okay if we shorten it to like not this function or not continuous or differentiable at x equals 2, or do you want to write it out?
So usually they will ask you one or the other. I'm showing you both so that all the bases are covered. They usually will not ask you both of these in one question. They'll ask you one or the other. I'm just showing you everything. All right. Number 4, is it continuous? Yes. So continuous everywhere. Is it differentiable? No. All right. So not differentiable at x equals -3. And guess what we're gonna write, guys? Limits, yay! Limit x goes to -3 from the left. Limit x goes to -3 from the right. How's it gonna be set up? You guys tell me. All right, f of x. Good, minus f of -3 over. Oh, good. I was hoping somebody would get that. Why is it x plus 3? Two negatives. Beautiful. Now, don't finish it because I'm going to show you what to write on that. As you look from the left, like when we did this one, we're going to compare and contrast. We know this slope is -1. It's linear. You can just see down 1 over 1 and that this is +1. Can you tell exactly what it is from this? No. But if I draw in tangent lines, what kinds of slopes do they have? Negative. So you can just do this, less than 0. And on the other side, if I mean, I don't know exactly what it is, but if I start drawing in tangent lines, yep, they are positive, so greater than 0. And that's good enough because you can't tell exactly from the graph, and they'll accept that on the AP exam.
So we do that for number 2 as well.
I was actually just about to say that. So up here, instead of equals -1, you could just say less than 0, and you could say for this one greater than 0. Actually, you could do the same thing here too, because do you see how if I draw in tangent lines on this side, like they're going down? Oh, well, actually this one, these tangent lines would also be negative. So you can't get away with that here because they'd both be negative. So I would put DNE for this one. But yeah, if you don't want to put an actual number, you can just put greater than 0 or less than 0. Okay. And then I ended with the easiest one. Is this continuous?
Yes.
Yes. So continuous everywhere. And is it differentiable? Yes. So differentiable also everywhere.